Okay.
full screen. There you go.
Right. Well, thank you again to Dimitri and the whole organizing team for inviting me. What I'd like to do today is just kind of summarize what's been happening recently in the sort of fossil spider world, in particularly the question of where did spiders evolve from, because this I think is a topic which is of general interest to all of us. Just to put things into a wider context, I'm sure most of you realize there are 16 different orders of arachnids. 4 of them are extinct and the other 12, of course, are still with us. The 4 extinct ones are here, the ones in grey. That's the Uraraneads, Trigonotarbids, Haptopodids and the Phalangotarbids. These, I say, are extinct groups. They're only known as fossils. What we can do as a general phylogenetic picture, though, is kind of take half of them out and say that half of the arachnid orders that we know today either have or are believed to have book lungs, and they form a group together which has often been referred to in the recent literature as the Arachnological. And actually, this is probably a fairly reliable, robust group now in arachnid evolution. And if we were to sort of plot a tree of it, we get a picture, probably something like this. I think most workers would be reasonably happy with this basic phylogeny here. And what I want to do is also have a time axis here on the left and just kind of see if we can build up the picture of where the spiders came from, put this into some sort of temporal context in terms of deep geological time. Now, the first thing we do as arachnid paleontologists is ask ourselves, when are the oldest records of all of these different groups? And we can plot those on here, something like this. So, for example, the oldest scorpions are still the oldest arachnids that we know, and they date back to the middle of the Silurian period, about 435 million years ago. The oldest spiders, by contrast, are rather younger. They're only known from about 315 million years ago. And what I think you can see from this basic picture here is that we have a rough plan now for when these groups might have diverged from each other, but there are a couple of notable gaps here. For the schizomids, the longer gap towards the right, this is a group that we would expect to be present in the Carboniferous, but the oldest ones we find from the mid-Cretaceous, from Burmese amber. And this is probably fairly easy to explain. Schizomids are small animals, they've got a soft cuticle, they tend to live in caves or in leaf litter, and so the chances of them being preserved are probably quite small. What's kind of interesting is that the other gap we have in this tree here is actually with the spiders. There is a group which Martin mentioned in his talk earlier called the Uraraneads, which are probably the sister group of the spiders, and they go back to the mid-Devonian. So that suggests that the spiders should have split from them at about this time as well. And it means that there is still a bit of a gap here between the mid-Devonian and the end of the Carboniferous. Now, the next thing we do is we go into the literature, we have a look at what the molecular biologists are telling us. So what I've done is taken the same tree here and just taken some of the estimates from the molecular clock data from the literature. And what we see is that the basic picture is more or less the same. Some groups are potentially going to be pushed back a bit further. So you might suggest that the oldest arachnids could even have been around towards the end of the Cambrian or the beginning of the Ordovician. At some point around the Ordovician or the Silurian, the arachnids must have made that jump onto land. Whether that happened once or on multiple occasions, this is something that's still being actively researched. And the interesting thing, though, going back to our spider question, is that the molecular data is actually telling us the same story as the fossils in some way, in that there's a kind of a range of dates from the molecular biologists, which more or less matches this gap in the fossil record. So again, the molecular data would be suggesting there should have been spiders around in the Devonian. Okay, that's just a sort of overview of where we are. What I'd now like to do is literally walk you through the tree and just explain what the main characters are which are defining these various groups within the spiders and their closest relatives. So we can sort of see how the spiders are coming out of this larger Arachnological group. Arachnological is actually a very easy one to define. You can find the similar names in the older literature, but it's really the molecular data in the last few years which has confirmed that this is a likely clade. But the best morphological data or evidence is, of course, the presence of book lungs, which we see in scorpions and, of course, in the spiders and their closest relatives like whip spiders and whip scorpions. It differs slightly in the number of book lungs, but the book lung is their common synapomorphy, or their defining character. Now, what's kind of interesting, actually, in the last couple of years, the molecular data is even suggesting that perhaps pseudoscorpions are closely related to scorpions as well. This wasn't a very popular theory in the past because the idea was that these claws are just kind of convergent, but it does actually seem that there is some molecular support for this, and even a clade name called Panscorpioides has been suggested. So we could even consider that these animals belong in this group as well, although in course in this case the book lungs must have been turned into trachea or replaced by trachea, and that's not such a huge problem because we know, of course, from spiders that they've done this as well. Many of the higher spiders or the more derived spiders have also turned one pair of book lungs into a tracheal system. Okay, but we can leave those two out. Now we're going to concentrate on what's widely known as the Pantetrapulmonata. And this is probably the least controversial group in the whole of arachnid phylogeny. In many ways, authors such as Pocock got it right in the end of the 19th century. And all of these arachnids share a number of features. For example, they have a sort of narrowing between the prosoma and the opistosoma. But perhaps the best character for these groups is firstly, because they're called Pantetrapulmonata, that they have 4 lungs, at least in the ground pattern. As I say, there's some of the spiders, of course, have turned the second pair of lungs or even the first pair into trachea. Or have lost them completely. And the other character which these animals have in common is the so-called clasp knife or pocket knife chelicerae. And that basically means the chelicerae and the fang that we see in spiders that sort of folds out. It's not a claw-like chelicerae that you see in a scorpion. Okay, if we take out this extinct group Trigonotabida, we do have a little bit of a problem here. This group that's left over, the Tetrapulmonata, which was defined by Jeff Schultz back in 1990, is a little more difficult to define in terms of morphological characters. But I would like to suggest 2 possible solutions. The pictures here are actually of these extinct Trigonotabids. And what you can see in the mouth parts on the left side here is that the first pair of leg coxae have a kind of projection or endite. So you can see these little sort of, this is the one in blue, these bits going in towards the mouth. There's like a little projection, almost tooth-like projection from the first pair of leg coxae. And you don't see that in whip spiders, whip scorpions, and spiders. So the loss of these endites is one possible character which might define Tetrapulmonata. The other one relates to the eyes. What we can see on the right side is a close-up of the eyes of a Trigonotabid from the Devonian. And what you can see there is the eye tubercle on the lateral eye tubercle. And there seems to be a kind of 3 areas on there, which might correspond to the 3 large lenses that are typical for these arachnids today. But you also see like a kind of row of smaller lenses in between. So we could argue that these animals have a sort of semi-compound lateral eye. It's like they've retained from horseshoe crabs some of these multiple lenses that would have been in the original lateral eyes. And if you look at the modern tetrapulmonates, spiders, for example, you have the pattern of usually only having 8 eyes, so the 2 and plus 3 and 3. And the only ones that are different to that are the whip scorpions, which have 3 large lenses and perhaps 2 very small lenses in between. So this character of reducing the lateral eyes is perhaps also something which can define the Tetrapulmonata. But we're dealing here with 2 reductive characters, which is always a little bit problematic in phylogeny, but that's perhaps the best I can offer at the moment. Now, these animals, this is the whip spiders, the whip scorpions, and a group called the Haptopodes, which is only known from a single Carboniferous fossil. These make a group called the Schizotarsata. It's a bit of a mouthful, but basically they all have a shared character in the second to fourth pair of walking legs. The tarsus is always divided into three parts, or tarsomeres. And this seems to be a reasonable character which defines this group here. And that leaves us then with the final group, which is the spiders and their relatives. And in a paper a few years ago with my colleagues, we proposed a name Cerciodistata as a clade name for this group. And it's basically the spiders and this extinct group called the Urarioneids. And their defining character is the presence of silk glands in the opisthozoa, which open through spigots. Okay. Now, Martin showed this briefly also in his presentation, because you could see how important the presence of spigots and silk glands is going to be for the story here. Back in 1991, Paul Selden and Bill Shear described these fragments of cuticle and suggested that this animal called Atacopus could even be the oldest spider, because it has spigots which would have produced silk. A bit later, they kind of looked at this material again and actually worked out that these spigots aren't actually sat on a spinneret. They're probably just on like a kind of a ventral sternite or plate on the opisthozoa. And these fossils, these cuticle types, are also associated with a small flagelliform telson, a bit like what you would see in a whip scorpion. And they also kind of combine this with another intriguing fossil from the Permian, which looks on first appearance is a bit like a spider, but it doesn't appear to have any spinnerets, and it also has a long flagelliform telson. And they suggested that these two animals should really be separated out and treated as a separate extinct arachnid order, and that's the Urarioneida. Okay, so we're kind of closing on our tree a little bit, and we can pick up a phylogeny something like this. You have the Urarioneids and the spiders sharing the character of opisthozomal silk glands, and the spiders, in this case, would have spinnerets and have lost the telson. This seems to work quite nicely, but I've left a bit of a gap because it would be nice to sort of fill in the missing links. And then in 2016, together with my colleague Russell Garwood and some other workers, we described a fossil called Idmonarachne. Now, Russell works at the University of Manchester, and he's one of the world experts in this kind of micro CT technology. So what Russell will do is take these fossils preserved in ironstone nodules, and he scans the hole in the fossil where the original animal would have been. And then you can turn this sort of negative into a 3D positive, and you get an idea of what the original specimen would have looked like down into the details of the legs. And Idmonarachne, again, looks on first appearances really quite spider-like. You can see the chelicerae here marked in dark blue, and then the pedipalps and the legs. But interestingly, on the opisthozoa, we don't have any evidence for a telson. And also, we don't have any evidence for spinnerets, even though we used the best possible scanning technology. There was really no evidence of spinnerets at all. So if we're going to combine that with our tree that we're building up here, we got really quite a nice progression of characters. We start with our Urarioneids, everything then has their silk glands. We get to the stage represented by Idmonarachne, where the telson becomes lost. And then eventually the spinnerets evolve, and we get the spiders as we all know and love them. And then this one appeared, which again Martin showed in his talk. Chimaerarachne really kind of put the cat among the pigeons a bit. It's clearly a spider. It's got a male palpal organ. It's got really quite nicely developed spinnerets, and it also has a tail. So how do we fit this then into our phylogenetic system? Also, what's interesting about Chimaerarachne is we can perhaps use it to try and understand where some of the characters in spiders evolved from. What was the kind of the ground pattern of spiders? Let's start with the male palpal organ. Here on the bottom, highlighted in red, what you have is a kind of a sort of symbiont, is kind of like a fork shape. It's kind of like a bifurcate. And the actual embolus is just a sort of a simple straight projection. There's nothing really very, very impressive about it. So in many ways, the male palpal organ is quite simple and is quite similar to what you might see in various megalomorph spiders and also basal araneomorph, something like a philistatid. And what it's not like, where it's very different, is it's not like the palpal organ of a mesotheled spider here on the right. These are actually quite complicated. So that was something that was quite interesting. Now, this picture we've seen quite a few times today, and perhaps the take-home message from John and Michael's work here is that spinnerets are very, very important in spider classification. This again goes back to Martin's talk earlier and the importance that spinnerets have in our understanding of spider evolution. And Chimaerarachne is actually really quite interesting because here what you see is that it has very well-developed anterior lateral spinnerets. It has very well developed posterior lateral spinnerets, but it doesn't have any evidence for posterior median spinnerets. And where you'd expect the anterior median spinnerets, you only have two kind of little humps bearing setae, which, yeah, maybe they were producing silk, maybe not. It's really quite difficult to tell. And the important thing here is that this does not really conform to what we would have expected from a spider ancestor or the spider ground pattern, if you like. You may know there was a famous paper by Marples where he suggested that the original spider ought to have had 8 quite well-developed spinnerets, 2 anterior laterals, 2 posterior laterals, median, and so on, and that this basic pattern then split up into the kind of patterns that we see in the modern spiders today with cribellite and ecribellite forms and so on. Chimaerarachne doesn't really fit into this model. So we're faced with the question, is Chimaerarachne showing us what the actual original condition of the spinnerets was like, or is this actually a derived animal in some ways that has moved on from the original condition? And that's a question we haven't really got round to answering yet, and we perhaps need more fossils to answer that. And again, something that Martin mentioned is another thing that's kind of interesting is that the spinnerets are actually in a rather posterior position, which is, again, what you'd expect from a megalomorph or araneomorph spider even. And it's not exactly the same as the position in mesothelials. So again, Chimaerarachne, in terms of its pedipalp, is showing us what we would expect a primitive spider might look like. But in terms of its spinnerets, it's actually showing something really quite different. Okay, and this is now our phylogenetic tree is becoming perhaps a little bit complicated. Chimaerarachne, as I say, you really do have to treat it as a spider because it has the apomorphies of palpal organ and spinnerets. But it suggests that there may have been multiple losses of the telson. If the Edemonarachne is something close to spiders, it's lost a telson, and also the modern spiders have lost a telson. So again, maybe this is a character which has been lost on multiple occasions. We can perhaps make some suggestions why this happens, that once these animals start building webs, a telson maybe gets in the way and then there's more trouble than it's worth. But these are kind of hypotheses. This is something we really want to perhaps look at in the future. Now, another important step was Paul Selden revising the Carboniferous spiders. And Paul published this lovely monograph earlier this year, where he basically went through and looked at everything which has been called a spider from the Carboniferous. This has been a very, very important piece of work for understanding spider origins, because what he showed is that some of these spiders clearly are mesothelials. This is a very nice one from America. And you can even see here at the bottom some evidence of their spinnerets. What's kind of interesting, though, is that some of these animals which have been described historically as spiders may not actually belong in this group. They look perhaps a bit like spiders on first impressions, but when you look at them carefully, we don't find proof that they actually belong in Aranea. Now, for a bit of fun, I thought I'd try and do a reconstruction of what one of these animals may have looked like. This is one called Eoteniza. It's a British fossil. It comes from the English West Midlands, from Coseley near Dudley. And it would have been about 315 million years old. And again, you taking the fossil and making a bit of artistic license for the legs, we get an animal that perhaps was rather spider-like, except when you turn it over. If you look at the underside, there is no evidence for spinnerets. There's not even any evidence for little holes where spinnerets might have been and then have fallen off. So you might have an animal that looked rather spider-like, but still seemed to have actually lacked the spinnerets. And so this is kind of interesting as well. We're sort of building up a picture here of a whole group of spider-like fossils. At the end, we don't know, were they a clade? Was this a group which lost the tails on one occasion? Or is this something which has happened on multiple occasions? And these fossils, unfortunately, are not always well preserved enough that we can really fit them confidently into our phylogeny here. But I think what's kind of interesting is that we can almost make a comparison, if you like, with human evolution. I'm sure we all know this classic progression from monkey to man, and although it's a popular image, it's probably incorrect. What we have on the right is a rather more complicated picture where it's actually quite hard to kind of pick your way through the tree and actually find the groups which actually led to the modern humans. And I suspect we have something similar going on in the spiders as well. I think perhaps my take-home message is that it was really quite an interesting time to be a spider during the late Devonian and the early Carboniferous, because there would have been several lineages around at that time, at least one of which led to the modern spiders. Another one seemed to have been kind of like blind alleys that maybe went extinct at some point between the Carboniferous, perhaps even the end Permian mass extinction. Okay, just to finish off, just to give you an idea of what's coming next, we're doing some more work with Russell here. This is a provisional scan of another fossil from Mont-Solimines in France, Carboniferous in age. And again, it appears to have some spider-like characters. We hope to work this up and hope that we can actually pick up some more detailed fossils from the Carboniferous, which might help us to show where they actually fit in on the tree. Some of these specimens that are simply just kind of squashed, you can't really get a lot of characters from them. The other one, again, picking up on something from Martin's talk, is that there are more interesting spiders coming out of Burmese amber. This is one that was in a private collection. We've now purchased it for Berlin. Let's kind of just take a closer look at it. And what we see here is that it has a segmented opistosoma, which suggests it's probably a mesotheled. But again, a bit like the spiders that Martin showed, the spinnerets are very much concentrated towards the posterior end of the body. Now, one could say, well, maybe these things are just juveniles. A recent paper was published by Huber and Haug, and what they showed is, here with the red arrow, that some of the earlier instars of mesothelials actually have the spinnerets towards the back of the opistosoma, and during development, during ontogeny, they do tend to shift forward into a more anterior position. But the thing is, in this case, we don't have a juvenile, we have a mature male. This is actually has a very mesothelial-like pedipalpal organ. So it kind of backs up what Jörg Wunderlich was saying, that perhaps the original condition in the mesothelials is that these spinnerets were towards the back and that they moved forward in the modern mesothelials. Why that's interesting, why that's possibly problematic is, as a final thought, the original idea was that spiders evolved their silk in the first instance to make the egg sacs. And this was supposed to be the explanation for why in mesothelials the spinnerets were pushed forward, that they were close to the genital opening, because their first function was a genital function, either making a sperm web or making an egg sac when the eggs are being laid. But perhaps this wasn't the case. Perhaps the spinnerets did actually start further back, and if so, why? Thank you for your attention.
Thank you, Jason. We have 6 minutes of time still, so perhaps if anybody has any questions. We've got a question from Ivan here. Hang on. So that miniaturization, yes, that's certainly a possibility. Chimaerarachne is quite a small animal, and this is again going to be a problem in the fossil record. Amber
only trap small animals because big animals can get out of amber. It's very rare to find a large spider in amber because they can usually free themselves from this type of preservation. So we're probably restricted in terms of amber fossils for finding out what we're going to have to use small animals, but that certainly is a possibility that it's a size problem. What of course will be interesting is to find a Chimera arachne-like fossil that's even older, perhaps from the Carboniferous. They ought to have been there. That's what the phylogeny is telling us, and perhaps, you know, with these CT scans, we might eventually find some earlier examples of what a Chimera arachne-like fossil would look like.
We've got another question here from Martin asking if Chimarachne spinnerets look a bit like Hepafella, isn't it, missing the PMS?
Yes, that's interesting. I mean, I suppose the question will be, why is it missing in the modern animals? I don't know enough about the mesothelials to say whether the spinnerets have different purposes. Are they using different spinnerets for the egg sac, and they're using other ones for the tripwires? I don't know. That's an interesting line of thought. You know, have they lost some of their spinnerets because they weren't, you know, they were laying their eggs differently, or because they were had a different type of lifestyle? I hadn't really thought of that, to be honest.
And an interesting question from Paul, who muses, maybe there is Chimarachne still alive today.
It'd be lovely to find one. That would solve a lot of problems. It's very interesting. There are a lot of rather strange things living in Burmese amber. Whether any of these things, I mean, there's ricinuleids and things that really shouldn't be there, and whether any of these things are still hidden somewhere in Southeast Asia, I don't know. It would be fascinating to find one. But as far as we know, this is a completely extinct group. If you want it to be something a bit problematic, they're quite similar in some ways to palpigrades. If you look at the underside of Chimera arachne, they're a little bit like palpigrades, but that's going down a different line.
And we've got a question from Jonas Wolf. The